All right, now we're going to look at how much work and power was done by the person over time. So using the kinetic energy theorem, we can see that the work done, instantaneous work done, should be 1/2 times mass, okay, times the change in velocity squared. So it's going to be this velocity, the velocity now squared, minus the previous velocity squared, right? So we do this, make sure that's a good formula, yep. Extend it out, and we should see over time. All right, so we have some work done on the ball. It goes up and down, and it has these spikes when we hit the ground. So let's say work done by person. Work done by person is the work done now if we're in contact with the ball. Doing this, plot that one, and we can see that most of that stuff goes away where, all those spikes where the ball is in contact with the ground, that goes away, right? And we have two outliers here, so we're just going to ignore that for now, right? And let's talk about power. Power is the rate of work being done over time. So it's going to be the work now minus the previous work. Come on. Work now minus previous work divided by change in time. There. Okay. So this is dw dt, right? Let's go and plot that. And this thing is from that work. Okay. So now let's say power done by person. And that's going to equal this power times if we are in contact or not, right? Okay. So now let's do total work done by person. So the total work, if we look at basically how we're moving this ball, we're picking it up over our heads, and then we're forcing it to the ground still. So the force of picking it up times the displacement going up, and the force going down times the displacement going down is the total work done, right? So if we ignore the work done by gravity, we can say the total work done is the work done by the person. That's the absolute value of that. We use absolute value so that we ignore the direction, right? So absolute value of the person, the work done by the person now, plus the work done and the time point previously, right? So let that go, and we can go plot this one, right? And we can see that every single time the person picks up and slams the ball, we get some work done by picking it up, and then the part where we're slamming it down is where we're doing the most work, right? We're changing the velocity the most. So this little region right there, this little bump, that is us picking it up, and then this is us slamming it down, right? Okay. So let's go ahead and modify this plot real quick. We start at 10 seconds. We're going to end at like 28. All right. So we can copy this, and then let's do the same thing for power. So total power. All right. I think we just copy this over, I think. Yeah. So this is going to be absolute value of the power now plus the previous power. Do that, and we can plot this one, right? So it looks like this first jump in power is odd. This might be different for every lab group, but you might have those jumps in work done over time, and for some reason it may show up as some kind of discontinuous or like a bad signal for power. Just don't worry about it. This is the signal over here is where we really what we really care about. So for some reason it jumped, but we're going to ignore that. Okay. Cool. So that is question 1, part B and C done. Next, we're going to look at how much energy did the ball absorb.